Imagine I hand you a bottle in the laboratory and ask, is the substance inside an acid? You confidently reply, first, let me check if it contains hydrogen. You examine the chemical formula, no hydrogen, not a single hydrogen atom. You smile and say, it can't possibly be an acid. But then, the substance reacts exactly like an acid. Wait, how can something behave as an acid without having a proton to donate? Has chemistry broken its own rules? Not at all. It simply means the rules have become bigger. Today's lesson will introduce you to one of the greatest breakthroughs in chemistry, a theory that changed how scientists think about acid bases, chemical bonding, catalysis, coordination compounds, and countless industrial processes. Welcome to the fascinating world of the Lewis theory. By the end of this lesson, you will understand why this theory is considered the broadest acid-based theory and why electron pairs, not protons, take center stage. Hello everyone, welcome back to where we want to make chemistry to be made simple, where complex scientific ideas become simple, practical, and unforgettable. Whether you are preparing for WAEC, GC, NECO, JAMB, IBM, DPEP, or studying chemistry at the university level, this lesson will deepen your understanding as one of the most important topics in general and inorganic chemistry. We've looked at Arrhenius, how Arrhenius focused on water, Brønsted-Lowry focused on protons. Today we are taking one step further. We are shifting our attention from protons to something even more fundamental: electrons. Science grows because curious people ask difficult questions. For the earlier 20th century scientists or chemists had already accepted the Arrhenius and Brønsted-Lowry theories. Those theories explain many acid-base reactions beautifully, but not all. Researchers discovered reactions that clearly behave like acid-base reactions, yet no hydrogen ion were transferred. Some reacting substances didn't even contain hydrogen. According to the existing theories, those reactions should have been impossible, yet they happen every day in laboratories. One scientist refused to ignore this puzzle. His name was Gilbert Lewis. In 1923, Lewis proposed a revolutionary idea. He suggested that acids and bases should no longer be defined by hydrogen ions. Instead, they should be defined by electron pairs. That single idea transformed acid-base chemistry forever. The Lewis theory is remarkably elegant. It has only two essential definitions. A Lewis acid is a substance that accepts a pair of electrons, while Lewis base is a substance that donates a pair of electrons. Notice something extraordinary. There is no mention of hydrogen, no mention of protons, no mention of hydroxide, or even water. Only electrons matter. Whenever one substance provides an electron pair and another substance accepts it, the Lewis acid base reaction has occurred. This is why the Lewis theory explains so many more reactions than the earlier theories. Before we continue, let's understand what an electron pair actually is. Electrons occupy the regions around the atoms called orbitals. Sometimes two electrons occupy the same orbital. These are known as electron pairs. Some electron pairs participate in chemical bonding. Others remain attached to one atom without forming bonds. These are called lone pair or non-bonding electron pairs. These lone pairs are extremely important because they can be donated to atoms that need electrons. Whenever that happens, chemistry creates entirely new molecules. Let's examine one of the most famous reactions in chemistry. Boron trifluoride reacts with ammonia. At first glance, nothing seems unusual, but look carefully. The boron atom in BF₃ forms only 3 covalent bonds. That means it has only 6 electrons around it. Its octet is incomplete. Because boron lacks a full octet, it has an empty orbital available. In other words, boron is electron deficient. It looks for an electron pair to complete its valence share. Now look at ammonia. Nitrogen possesses one lone pair of electrons. That lone pair isn't involved in bonding, it is available. As the molecules approach each other, the nitrogen atom donates its lone pair to the boron atom. Boron accepts it immediately. A new bond forms. This special bond is called coordinate covalent bond, also known as dative covalent bond. Unlike an ordinary covalent bond where each atom contributes one electron, a covalent coordinate bond is formed when both electrons are supplied by the same atom. The product is written as what you are seeing on the board. The arrow points from the electron donor to the electron acceptor, showing the direction in which the electron pair is donated. Now ask yourself, who accepted the electron pair? BF₃. Therefore, BF₃ is the Lewis acid. Who donated the electron pair? NE₃. Therefore, NE₃ is the Lewis base. no proton moved, no hydrogen ions was transferred. Yet this is a perfect acid-base reaction according to the Lewis theory. The Lewis concept extends far beyond BF₃. Consider aluminum chloride. The aluminum atom is also electron deficient. When chloride ions donate an electron pair, complex ion is formed. Now think about silver ions. Silver ions readily accept electron pairs from ammonia molecules, producing the complex AgNH₃. These reactions are fundamental in coordination chemistry, analytical chemistry, and catalysis and industrial chemical process. The Lewis theory explains all of them with remarkable clarity. Why do chemists consider the Lewis theory the broadest? Because it includes almost every Brønsted-Lowry acid-base reaction. Whenever a proton accepts an electron pair, the Lewis concept still applies, but it also explains the reaction where no proton exists at all. It provides the foundation for understanding 1. The coordination compounds, the transition metal complexes, the organometallic chemistry, catalysis, metal-organic frameworks, MOS, semiconductor chemistry, material sciences, nanotechnology, industrial synthesis, biological meta centers. So this is why advanced chemistry relies heavily on the Lewis acid concept. Let's place the three theories side by side. Arrhenius theory asks, does the substance produce H3O+ or OH- in water? The Brønsted-Lowry theory asks, who donates the proton and who accepts it? Lewis theory asks, who donates the electron pair and who accepts it? Notice each theory becomes broader than one before it. Chemistry evolved from focusing on water to protons to finally to electrons. So the Lewis theory is not merely an academic idea, it is an essential part of the modern science and technology. Lewis acids are used in petroleum refining, polymer production, pharmaceutical synthesis, organic reactions such as alkylation. Lewis acid-base interactions are also central to designing advanced functional materials including MOS, used for gas storage, capture, catalysis, drug discovery, and environmental remediation. And chemists design new catalysts, construct coordination compounds, or investigate molecular interaction. They often begin by asking a Lewis question: who needs electrons and who can provide them? Let's log this into memory. Remember these rules. Lewis acid accept an electron pair. Think, I need electrons. Examples are the BF₃, the AlCl₃, the Ag+, the Fe3+, Cu2+. What about Lewis base? This base donates an electron pair. You think, I have a lone pair to share. Example of Lewis bases are ammonia Na3, H2O, OH-, Cl-, Cn-, just mentioning few of them. A comes before B. Acid accepts, bases brings, that donates electrons. That's a simple way to remember. That simple association can save valuable marks in examination. Now it's your turn. Answer this question in the comments. Why is BF₃ classified as a Lewis acid? Why is Na3 a Lewis base? What is a coordinate covalent bond? Name another Lewis acid that does not contain hydrogen. I look forward to reading your answers and discussing them with you. Today we've reached the broadest explanation of acid-base behavior in chemistry. We discovered that acids are not limited to substances that release hydrogen ions, and bases are not limited to something that produces hydroxide ion. Instead, chemistry reveals a deeper principle at the heart of countless chemical reactions, like the movement of electron pair. Whenever one species donates an electron pair and another accepts it, Lewis acid-base reaction has occurred. This elegant idea connects simple classroom example with cutting-edge research in catalysis, coordination chemistry, nanotechnology, material science, and industrial innovation. As you continue your journey in chemistry, remember that every new theory expands your understanding rather than replacing what came before. Arrhenius gave us the foundation, Brønsted-Lowry broadened the picture, the Lewis provided the most comprehensive framework for interpreting acid-base behavior. If this lesson has deepened your understanding of the Lewis theory, support this platform, this channel, by liking this video, sharing it with other people, and subscribing for more engaging chemistry lessons explained with clarity and real understanding. Follow me for more original content. I am Omotola Fayomi. God bless you. More cares. Bye.